All right, welcome to AP Chemistry. This is your first unit of AP Chemistry curriculum. So we're going to start on Chapter 1, and this is going to be a lot of review, but it's important review because we're going to learn how to record numbers, how to use the language of science, how to use units to describe your data, and that's all stuff that we'll use throughout the whole year. So starting with the scientific method, this is just a general way of doing science, and it's not really set in stone. A lot of teachers teach that you do first you do this, then you do this, and they teach it as a sequential list of steps that scientists take. And in reality, science is a lot more circular, where you try something and then it doesn't work, so then you tweak it and you try something new, and then you collaborate with a different scientist, and it's a lot more complex than what most science teachers teach. But as an amateur scientist, it's a good place to get started. So as we start to come up with your own experiments throughout this year, it's a good general framework for how to set up your experiment. There's a few terms here, theory versus a law. A lot of people struggle with those two. So a theory versus a law. Highlight those two words. A theory is an explanation for why something happens. So why is the key word there, but it changes. So we don't always know exactly why something happens. We just use our experiments to try to explain things. And theories have changed throughout the year. We used to think, or throughout our lifetime. We used to think the world was flat, and now we think it's more of a sphere. We used to think that the universe was geocentric, that we were the center of the solar system, and now we think it's more heliocentric, where the sun is the center of the solar system. So a lot of theories can change throughout time. Laws are kind of set in stone. So laws are something that you have observed so many times that you consider it to be truth. So for example, you have never woken up and the sun didn't shine. Now it's not the sun that's coming up, it's the earth turning, but the earth has never stopped turning. So, or same way with gravity, you've never held a ball up and then let go and it just floated in the air. So it's observing things that have happened so often that we consider them to be truth. And it's more of the what is happening, but it's not explaining why that thing is happening. So theory is the why, law is the what. All right, the next thing is talking about measurements. And like I said, this is going to be really important when we start our experiments, and we're going to do some virtual experiments, even if I can't see you. So the first thing is to be sure that you always have a unit on your number. And this takes a little bit of practice. If you had me for honors chemistry, you hopefully got in the habit of putting units on numbers, because otherwise you get a lot of points taken off your lab write-ups. And that's basically because a number is meaningless if you're not telling me what that number is. So anytime you turn in a lab write-up, be sure to make sure that your number and your unit are both together. The next thing we're going to do is scientific notation. Almost all of your numbers in AP Chemistry will be in scientific notation. So in chemistry, we deal with really big numbers and really small numbers, and it's really hard to read a number that has a lot of digits in it. You have to sit there and count how many zeros you have or how many places it is till you get to the decimal, and that's just annoying. So instead, we can use this system where we multiply it by 10 raised to the power of something, and then that power tells us how many places to move the decimal. So first of all, it has to be between 1 and 9.9, and then it'll be times 10 to a power. So for this first example, we have 53,000. You have to first bump the decimal that is on the end of the number, bump that decimal until it's between 1 and 9.9. So if we bump it one place, it's still too big. Keep on bumping it. Once you get to 53, it's still too big, but 5.3 is perfect. So 5.3 times 10, and then you just raise it to the power of however many places you moved it. So 1, 2, 3, 4 places. And then the last thing you need to check is the exponent on the 10. The sign on the exponent tells you which direction the decimal went. So a positive exponent means you go to the right, a negative exponent means you go to the left. And so for this number, because the value of the number is really big, we're going to keep it as a positive exponent. All right, let's do the next one. Bump that decimal until you get 2.3, because 2.3 is between 1 and 9.9. Times 10, and then let's count how many places. 1, 2, 3 places. But because this is a small number, you do need that negative on there, because it will tell you to move the decimal to the left. So a negative exponent says move the decimal to the left to get the real number, and positive means go to the right. And that's it for getting into scientific notation, but now let's go backwards. So for this first number, 4.3 times 10 to the negative 6, we're going to bump that decimal 6 places to the left. So 1, 2, 3, 4, 5, 6. Let's add a leading 0, and this is the actual number. And notice that to identify what the value of that number is, you have to sit there and count the zeros, which is annoying, and that's why we don't do that. Usually we write it in scientific notation. And then for the last one, and the reason I knew to go to the left is because the exponent was negative. For this one, we're going to go to the right 8 places. So 1, 2, 3, 4, 5, 6, 7, 8. Let's add some commas so you can see it a little better. So 609 million is also written as 6.09 times 10 to the 8th. All right, the next one is allowing you to see why we do this. So you can see the magnitude of the numbers. So if you take a look at number 5, the first one has an exponent of -3 and the next one is -9. So it's really tempting to say, oh, 7.9 is bigger than 4.8. But really it's not the number itself that's important. It's the value of the exponent on the 10, because moving something a decimal place changes something a lot. And so if you can see, the first one is 10 to the -3, so you would only bump it 3 places to the left. The second one is 10 to the -9th, so you would bump it 9 places to the left. And so this one is a bigger value, even though the -3 looks like it's smaller, because 3 is smaller than 9. And the same thing for the next one. Again, we're given negative exponents, which means bump it to the left. This one, you're only bumping it 2 spaces to the left, and the second one, you're bumping it 31 spaces to the left. So that's going to be a whole lot smaller. All right, these are just some prefixes and units that you're going to need to be familiar with. So for mass, we usually use the grams or the kilograms. We don't use things like pounds. That's weight, which includes gravity, and we try to keep that out for chemistry. Length is used, we're going to use meter, so we don't talk in inches and feet usually in chemistry. We focus on the metric system. Temperature, we'll focus on Kelvin, and we'll talk about that later. Amount of substance is the mole, and then volume is the liter. So you'll need to go ahead and get these into your brain so that when you see a question and it says, what is the volume, you know what kind of units you're going to try to end up with. Or if they say something is so many meters, you know that they're telling you the distance. The next section is some prefixes, which is just another way to talk about big numbers or small numbers. So if we wanted to talk about how many atoms are in your desk, that's going to be so many that would be a huge number. It's hard to even wrap your head around how big that number would be. Or if we talk about the diameter of an atom, it's so tiny that it's hard to wrap your head around how small that number is. So it's useful to use prefixes instead of these really big and really small numbers. A lot of these you're probably familiar with from honors chemistry or from biology. There's a few new ones here that you might want to put a star by. So we have micro here, nano, and mega. We didn't do those in honors chemistry, so you might want to focus on those. Micro, that symbol it's called a mu, and it's a Greek symbol. It's kind of like an M and a U got married and had a baby, and that's what it would be. It's kind of a combination between an M and a U. And you can see the values of them on that chart. So in place of scientific notation, this is another thing we can do. For example, instead of saying that I have 1,000 meters, because 1,000 is kind of an annoying number, it's kind of big, I can just say that I have 1 kilometer. So 1 is a much easier number to use. So you should be able to use these conversions, and I have some common ones there to convert back and forth, just setting up a fence. And we did that in our review of honors chemistry. All right, and the last section for today is doing some dimensional analysis. This is a fancy way to say setting up a little fence. And we did that in stoichiometry as well, so you want to do some more practice to make sure that you can convert easily from one unit to another. That's a huge part of AP chemistry, is identifying what unit did they give me, what unit do I want to turn it into, and how do I do that. So if you just take a look at some of these examples here. So the first one says we have 23 kilometers and we're trying to turn it into meters. So you're going to start with what you're given, bring the unit down that you want to change into something different, and then put the unit that you want on top. Always try to set up your units on the fence before you plug in numbers, because a lot of times it's easy to flip numbers upside down. So set your units up and then ask yourself what the conversion factor is. So there are 1,000 meters in 1 kilometer. And then to calculate it, so you can see that kilometers cancels, and to calculate it, you can just type those in. So 23 times 1,000 will give you 23,000. So 23,000 meters and 23 kilometers is the same exact distance. It's just a different way to describe it. Let's try another one. So we have 400 nanometers nanometers down, and meters on top. I know that nano means 9, so that's how I remember it. And I know that a nanometer is tiny. It's a really small thing. So I'm going to put the 1 with the meter and then put 10 to the 9th nanometers down here because I know it takes a lot of nanometers to make up 1 meter. So notice the big numbers with nanometers. And I also know nano means 9. So this is the conversion factor. So then you just do 400 divided by 10 to the 9th. And your calculator will probably tell it to you in scientific notation. Let's take a look at example number 5. So this one says we have 65 moles per liter. And you do have to be careful when you have a fraction as a unit, you have to split it up on the fence because really what that's telling you is a ratio that you have 65 moles for every 1 liter. But they want the units to be in moles per milliliter. So we're not going to do anything with that unit of mole because we want it to be on top when we finish, and it's already on top. What we need to do is cancel the unit of liters. We don't want liters down there, we want to have milliliters. So I'm going to do this so that the liters will cancel. And then you can plug in your units. So 1,000 milliliters is equal to 1 liter. So when you divide that by 1,000, it would be the same value, but it would be in units of moles per milliliter. The rest of them you probably can do on your own. You should know how many. We can do just a couple. So like number 2, we're going from hours to seconds. So we have 4.3 hours. You could probably figure out how many seconds are in an hour, but if you get to choose the conversion factor, just choose ones that you can do without thinking too hard. So I know that 1 hour is equal to 60 minutes without doing any math. Then you can bring minutes down and turn that into seconds. Check and make sure your units cancel. I didn't cancel them up here. And hours cancels hours, and then you just calculate it through. So 4.3 times 60 times 60, and you get your answer. Let's do one more. Let's do number 3. That one has another fraction as a unit. So we have 5 meters per second, and we want to turn it into kilometers per hour. So we can't do both of these conversions at the same time, but we can do them all on the same fence. So I'm going to do seconds first. I'm going to bring that up to the top. And just because I can do minutes without thinking too hard, I'm going to go ahead and turn it into minutes first. And that cancels the unit of seconds. So right here I would have meters per minute. But I want meters per, or kilometers per hour. So now I'm going to bring minutes to the top, hour on the bottom, and be careful with your numbers. I see a lot of students that tell me there are 60 hours in 1 minute. So just make sure you plug in the number with the correct unit. And now we have hours on the bottom, which is what we want. But we still have meters on the top and we want it to be kilometers. So let's bring meters down. Even though meters is way over on the left and way over on the right, it will still cancel as long as it's on the top somewhere and on the bottom somewhere. And then we want to turn it into kilometers. So we can say that 1 kilometer is equal to 1,000 milliliters or meters. And then you just do the math. So 5 times 60 divided by 1,000. And that's it for this lesson. So on the progress check for today, if you go to Canvas, there's a worksheet that allows you to do some just calculations with scientific notation and some of these unit conversions to make sure you remember how to do that from honors chemistry. That's it, and I will see you tomorrow.